Hi Algebra students, today we're going to talk about the issue and methods of regression, and we're specifically just going to focus on linear regression today, but in this unit towards the end of the year we're going to be looking at multiple different kinds of regression. We're going to apply different functions from our library that we're learning about, like what was the most recent function we just learned all about? Parabolas. We're going to do parabolic regression this week, I think, as well. You can really use any function to do regression. The more advanced functions you use, the more assumptions are kind of going into it, but we're going to stick with the basics this year in general. So we're going to start with linear regression. In other words, relationships that look straight. In other words, data that's pretty straight looking. That doesn't mean it has to be all along one line though, okay? There's a few definitions you definitely want to get down over here. So what am I trying to define in that first sentence there, guys? What is being defined? Like, what should I underline? Regression. Regression is the statistical study of the relationship between variables. Sometimes instead of the word relationship, you'll see the word association. Okay? Those mean pretty much exactly the same thing. The association between two variables. Now, of course, there's not always an association between two variables. And when there is, you need to describe it with three features. Always three features, right? So this other word kind of creeps into the discussion sometimes as well. Sometimes people, and I'm sure you guys have seen this word used by the media, by all kinds of different sources in our society, correlation, and that's kind of a dangerous word. When you say correlation, you're talking about immediately a specific kind of relationship. People use this word, I should say, misuse this word all the time. If you use the word correlation, you're implying the shape of that relationship. You're implying that it's straight. So if it's not a straight relationship, it's some other kind of relationship, you shouldn't even use that word correlation. So that's a little bit dangerous. So be careful with that, okay? I'll probably try to trick you on the final with a multiple choice question about that. So correlation is just one way to talk about a relationship. When you say correlation, you're already implying it's straight. But we should pretty much always be addressing relationships with three features. So when we talk about those scatter plots over there, I'm going to talk about each one with three features. Those three features to describe a relationship in a scatter plot are shape. If you use the word correlation, you're already implying the shape, that it's straight or linear. The other feature is strength. And the final feature is direction. Now, some shapes don't really have necessarily a direction, but of course linear shapes do have a direction, okay? And most shapes have some kind of direction. What matters most is shape and strength, honestly. But anytime it asks you to describe a scatter plot, you should be going for those three features, okay? So, R is called the correlation coefficient. R is the one way to measure or diagnose how good your model is. R always has to be between -1 and 1. Why? Well, if R was perfectly 1, that would mean all of your points in your scatter plot are perfectly on the same line. So this is a perfect model. We usually don't live in a perfect world or a utopia, so pretty rare. The only way that that's possible is if you measured things perfectly, which pretty much isn't in the realm of human possibility unless you have really precise instrumentation. Yeah, so generally not possible. But the closer to perfect you are, the stronger your model is. Does that make sense? That's like 100% on the line. That's another way to think about R equals 1. 100% of the points are on the line. R equals 0 means like, man, those points are all over the place. Does that make sense? R equals 0, though, when you say R, once again, you're assuming that the shape is linear. So R equals 0 could mean a random scattering of points, or it could mean something that's like perfectly not a line. So that's a little bit more dicey, and I won't get into that too much this year. That's for more advanced classes. But for my AP Stats students, you'll see some questions if you stick around in the class where R equals 0 might not mean a random scattering. It might just mean something about not being a line. We'll see some questions like that eventually. Okay, so this we're going to say the points are pretty much randomly distributed. There's no linear pattern. If R is 0, or if it's anywhere close to 0, you know, like 0.2 or -0.1, anything like that. If r is -1, that just means, once again, that the relationship is perfect. Instead of going up in a perfect way, it's going down in a perfect way. Okay, so again, this is a perfect relationship. It's just a downwards perfect relationship. Okay? Also pretty impossible. But if you're close to 1 or close to -1, you've got a nice strong relationship. Okay? The last thing I'm trying to define here, what do you guys think? What's this last definition of? Line of best fit. Now, we're going to be looking at other curves of best fit, like the parabola of best fit, the exponential of best fit, the sine wave of best fit. But this is the first one we're looking at today. So a line of best fit is a line which you can use to make predictions. There's a whole lot more to this theory. You need a lot more math to really understand it perfectly. We're just going to be kind of eyeballing the line of best fit, and we're going to, if we see a relationship that's linear, we're going to try to draw it so about half of the points are above and about half of the points are below. Okay? So I wanted to look at these 6 scatter plots, talk about their 3 features, maybe estimate R, maybe draw the line of best fit, kind of estimated on a couple of them. So what do you guys think? Shape. Shape. Linear. Direction, Kyle, you said down. So we're going to say negative for the slope of the line. And strength? Strong, weak, moderate. You can use adjectives or adverbs like moderately strong. I liked moderate. This is actually moderately strong. It's not bad. So let's say that. This is linear, moderately strong or moderate. You guys are on it too. And negative in direction. Okay, that's what you'd say on this one. Estimating R is going to be a dicey thing. I don't expect you to be great at it at the beginning. I would say my guess on R, and I'm not the best at it either, but my guess on R, you can actually do it mathematically. We're not going to do that this year. If you had stats, I maybe did it mathematically. So R is about, I'd say, negative 0.75 or something on that one, negative 0.8 maybe. That's why it's not bad, okay? What do you guys think about the second scatter plot? Shape? Remember, 1 point doesn't determine the shape. This point's kind of an outlier. 1 point doesn't determine a shape or a trend. If you cover that up, what shapes does it definitely have? Linear. So this is, again, linear. It has a correlation. What's its correlation approximately? It's stronger than that one, right? So I bet this one's like in the neighborhood of 0.9 or better, and it's positive in direction. Okay? How do you draw the line of best fit? Once again, you'd like eyeball it with a ruler, and you'd say, how do you make it so about half the points are above and half are below? This guy's exerting a lot of leverage on the line and trying to pull it down. That's what outliers do. But basically, it'd be something like this, I think. If that guy wasn't there, it'd be tilted up a little bit, right? So there you go. I can put this one over here, probably something about right there. If I get half of them above, half of them below, I'm not playing dot to dot. That's key. This is not a highlights dot to dot thing. You guys know about highlights. I'm getting old. Okay, what do you guys think about this one? 3 features. Is that linear? No. Is it random? No, it's got a shape. What shape? That's a parabola, so we'll look at those later this week. It would have a parabola of best fit, but we're going to do that next time, okay? So shape is non-linear, at least. You could say non-linear or parabolic. Either one of those is good. Strong or weak or midway? I think it's pretty strong. I'd say that one's at least moderately strong again. It doesn't have an R that measures it, but you have this thing called R squared, which is like the same thing. So we'll look at that another day. Okay, direction, I guess we'd say down because it's a down parabola or negative. Okay? What do you guys think about this 4th scatter plot? Pretty random. I don't think this one has any particular shape. I think its R value would be approximately 0. Maybe it'd be like positive a little bit or something, but it's mostly random, okay? What about this guy? I think this one's linear. A little tougher call, a little more experience, but this one's linear. Looks like it. It's not great though. It's a weak linear one or a middle to weak linear one. The line's something like this. I think they're generally going up over time though. I'd say R on this one is probably like 0.4 to 0.5. Positive, of course, okay? Remember, always 3 features. What do you guys think about that last one? Yes, that is an exponential. We're going to look at exponentials as our last function and logarithms as our last two functions for this semester. So we'll be looking at those next. But it's clearly not, even if you don't know exponential yet, you know it's not a line. But it's clearly not random either. So I'm just going to go ahead and say not linear. If you said exponential, great. It's definitely not linear though, it's bent, right? How strong is it? Strong. It's strongly bent around this line. Actually, it's line. Around that curve, right? So not linear, I'm going to say strong. And it's going down, so I'm going to say negative. This is actually an exponential decay model, which we'll look at soon. Okay? But it's not linear, so you're not going to hopefully see any of those in this assignment. Coming soon. All right, let's get a couple real sets of data now. So here's another example of linear regression. Well, I guess I don't want to assume that it's a linear model until I look at the scatter plot, right? So we'll assume that we're going to just stick with linear models today before we move on to other types of regression models later this week. So we've got some temperatures. Temperatures in Ohio and temperatures in North Carolina. Looks like there's some numbers in there that tell me Fahrenheit. 70 degrees Celsius is really hot. You don't want to live in a place like that. It's like it'll burn you. So I'm assuming these are degrees Fahrenheit, even though I just pulled this off the internet. Okay, so first, we want to, when you're doing your assignment, scatter plot it by hand and do a good job. I'd either use graph paper or be very specific. To save time today, I'm just going to scatter plot this with my calculator. You guys know how to scatter plot something by hand, right? We're going to then use this calculator scatter plot and create the model first by hand. I need you to know how to do that. And then using our calculator. And then we'll use it to predict a couple values, okay? So let's first of all just create the scatter plot. Here we go. So I'm going to go into my calculator. Absolutely everybody needs to be doing this with me. So here we go. So I'm going to go to Stat. First of all, Stat brings up this menu. Then I go to Edit, which brings up this menu. You might have things in your lists. You might not have things in your lists. If you do, like me, go up to the top of the list, highlight it, and press Clear, Enter. Don't press Delete or your list will disappear and you'll have to pay someone to get it back. Saving you guys money. I go up to the top, I hit Clear, Enter. Now it's nice and cleared out. Now, when I first encounter a set of data, the most important thing is usually to try to figure out which variable is which. Don't just assume that like the thing on the left is x and the thing on the right is y, or top or bottom, you know. People make that assumption in lower level classes. It's not a good idea. So you always want to think what's independent and what's dependent. In other words, what is explaining the behavior of what else. Now in this case, since we just have temperatures in two different locations, I don't know if there's enough information to say if one is really explaining the other one. So we're going to kind of just pick randomly. But on every single problem of yours, there should be one that's kind of explaining the other one more, or at least most of those problems. Does that make sense? So I always want to think what's explaining and what's being predicted. The y is the thing that's being predicted or dependent. The x is the thing that's doing that explaining. Does that make sense? The explanatory variable. So in this case, I don't know, I think we can pick it either way, so let's just do it as Ohio for X and North Carolina for Y. No particular reason on that. I don't know how to pick between those two. So let's enter that data in our calculator. 31, 20, 65. The only reason I split that into twos is just so your eyes could follow it better. No other reason. Okay, I like to always check that my lists are of the same dimension, because if one of these is like a little longer, your calculator's going to explode and you try to tell it to do stuff. So it's like, hey, I only have half a point. So always make sure they're nice and even. You can look and see how many things are in your lists pretty nicely. If you scroll up to the last entry, it tells me there's 10 things in that list with this little index dude right here. That's pretty nice. You don't want to have to actually count how many things you put in, especially if there's a lot more than 10, as in many problems. Okay, so first thing we're going to do is just get a scatter plot rolling on this guy. So I'm going to go to y equals and make sure there's no function in there. I do have something, so I'm going to clear it. And then I'm going to go second y equals, which brings me to my plots. Plot 1 for me is already on, I bet yours aren't. So go into plot 1, hit enter, and make sure it says scatter plot. So that's the first thing, it says scatter plot, and make sure it says list 1 and list 2, because that's where we put our stuff. In more advanced classes, we often put lots of different things in lots of different places, and that's where you tell it what things to grab. Yeah? It's pretty simple. If you like big dots, use this one. If you like small dots, use one of the other ones. Doesn't matter, you pick what you gotta do. Alright, so now I'm going to go zoom. For functions this year, we've been using zoom what? 6. For data, this year and into the future, the best zoom option your calculator has is zoom stat, meaning statistics, meaning data. Does that make sense? So it'll do a nice zoom on this guy, so you don't have to figure it out yourself. So I'd start with a nice zoom stat, and it'll grab your scatter plot. Now this is a little bit dangerous, and I'm going to be going over what that danger is once we fall into the trap. We'll get ourselves back out of the trap, okay? So there's our scatter plot. Let's try to create the model now. That's the big important part, creating the model for the scatter plot. First of all, 3 features. Shape. It looks linear, I don't think it's bent. Strong, weak, moderate? Moderate. At least moderate. I'm going to say moderately strong. So good. Direction? Positive. It's going up. Positive slope. Yes, Lauren?
It just says invalid dimensions.
It's because you entered something wrong in your lists. Look, I'll try to help you once we're done here. So. Okay? So, there we go. How do we get the calculator to do the model for us and find the absolute best thing? And how do we do it by hand? So when you do this by hand, you're going to have this sketched on graph paper real nice. You're going to get a ruler, unlike what I'm about to do. And you're going to eyeball where your line of best fit goes, with about half above and about half below. Resist the urge to play dot to dot like right here. There's a lot of points in a row right here, but if I go like this, it's going to be a little too steep, isn't it? I've got to get all the trend in there. So I think something, you guys tell me if I'm thinking right, maybe like this?
Yeah.
It's not going to be perfect. We'll see how good a job we do when we create the optimal model with the calculator in a second. So I'm going to say something like this, trying to be straight. Use a ruler though when you're doing your assignment. Okay, now the next thing I need is I need the scale. When you do your assignment, you're going to have gone by a certain scale, so you don't have to worry about it. So I'm going to have to do a little work on this problem to get the scale out of my calculator. Where do I go to get scale? Window. Now that's what the calculator made. It's got decimals in it and stuff. Let's clean it up a little bit, but not much. I bet if we just go 16 to 70, that's good enough, isn't it? 5 sounds good to me. And then let's just go, instead of 40.39, let's go 40, right? And then like maybe 85 by 5s. And now we can start cleaning this up. So our graph scale, I don't know if it started like right here, we'll see. Is it started at y of 40 up to 85 by 5s, right? We'll remember that. And then right here we started at x equals 16, and we're going to go up to 70. I'm going to have to adjust those to go back to my graph. Notice I didn't really change it by just changing those a tiny bit. Let's see. Yeah, that looks about right, yeah? This should be right here. There we go. So, creating the model by hand. Here we go. The by hand y hat. Very important that you can do this by hand. I'll be checking to see that you can. Well, what is the equation of a line? You guys know that. Mx plus b. Why did I call this y hat instead of y? Well, because it's a model. It's not the actual y, it's something different. We're using a model to predict things. The hat means predict. Okay? Alright, so we got to figure out a slope and an intercept. So the slope I'm going to do first. I just pick some points so you can kind of see clearly. Do they have to be the actual points in the plot? No. In fact, I would avoid those. Find some spots on your line that you can see nice, like this one. Maybe right there. If we're going by 5, 16 plus 5 is 21, plus 5 is 26. And then how about we just go like, I don't want to go too close because then the goodness of my drawing might affect me more, but it doesn't really matter. The slope of the line is supposed to be the same everywhere if it's actually straight. I didn't use a ruler though. So I'm going to just go over here and say, what's this one? Let's see, 31, 36. I'm going to just go by tens, it's smarter. 36, 46, this is at 55, right? Okay, so I'm going to do my little slope triangle. So I've got to change, what's 55 minus 26? You guys tell me, you've got the calculators. Help me out. 29? Okay, that was pretty easy. Now I've got to go over here and see where these came to. That was 40, 45, 50, 55, 60, 65. That looks like maybe 66, doesn't it? So I'm going to say this goes up to 66. How big is that difference? 16. So my slope is going to be rise 16, run 29x. Y-intercept should be easy. Where does it look like this crosses? That's 40 and that's 50, like 49. There we go. There's my model by hand. Make sure you can do that. And on the first few questions, I asked you to do it both that way and the fancy way from the calculator using more advanced math. You don't have to know any advanced math to do it. You just go on here and you say, statistic. I'm going to get some of this junk off now so we can see.
Statistic.
Instead of going to my lists, I go over to calculate. Which one of those things do you think I want to use? Linear regression. It's in number 4 and number 8. It doesn't matter which one you use. It's the same thing. So linear regression, if you have a newer calculator to like bring up a menu, just make sure it says list 1 and list 2 if your menu pops up and you tell it to do it. There you go. In a second, I'll show you if R didn't pop up. I'll show you how to fix that in a second on your calculator. But let's write down the model. So here's the calculator's version. What's the calculator's slope? 0.6803. Notice, this is calculator throw up. If you write calculator throw up on your paper, that's not very useful. So make sure you change calculator throw up into like the actual model. Don't actually just write that junk down on your paper. Notice I'm taking the slope, which is the thing attached to x, and I'm taking this guy, 31.88, and I'm going to write down my R value. R was 0.911. See, it was pretty strong. It's really strong, actually. Go back to it. So there we go. There's the model the calculator got. How good is our slope? Well, I need to go 16 divided by 29 to see. 0.55, 0.68. Those are pretty close. It's not great, and that's what you're going to find. You want to do the best you can. I just drew it by hand, and you use a ruler, right? So that's not bad. My intercept's pretty wrong. 49 versus 31? What? What's going on there? Well, remember, we pressed zoom 9 to get this, right? Where are all these values actually at? Are any of them close to 0? So really, when the calculator zoomed 9, where's the real origin? It's not right here. It's like this way and this way. The real origin's like down here. So my line that went like this, we said it was 49, but if you actually had this drawn on graph paper, where would the real y-intercept be? Down farther. That's why this one's definitely the more trustworthy one. So that's something you've got to be really careful about. When you're doing by hand models, you've got to actually, if you do some kind of breaking the graph or zooming of the graph, you've got to be clear about where it actually crossed the y-axis. That's why zooming is dangerous. Okay? So be careful about that. That's about the only tricky issue on here, though, I think. This is definitely close enough. We did a decent job. If we'd have thought about how it needed to go down farther, we'd have done a better job estimating that as well. And if you use graph paper, you won't have to worry about that issue. Okay? So there we go. Let's make a couple predictions before we're done with this example, so you guys can start working on your assignment. So let's predict a couple things. Let's predict, number 1, the temp in North Carolina for, I don't know, 40 degrees in Ohio. Number 2, let's predict the temp in Ohio. Now let's do North Carolina first again. For 0 degrees in Ohio. And finally, let's predict Ohio for 60 degrees in Carolina, North Carolina. Okay, now which one of the models do you guys think is more accurate? We just talked about that. Obviously not that one. Okay, so we'll use the calculator model. When you're doing your predictions, use your calculator model on those, okay? Let's see. So, what do we got to do here? Well, you just plug in x's or y's. You just got to be clear about which one's which. That's why you label things. Is this an x or y? Predict the temp in North Carolina for this in Ohio. This is in Ohio. This is an x. Label it. So all I've really got to do is stick it in for x and be done. I'm just going to do that on my calculator. Yeah, super simple here. So I'm going to go 0.6803 times 40 plus 31.881. There we go. So there's my first prediction. So we predict, or not, I'm not going to say we, I'll just say our model predicts about 59 degrees Fahrenheit in Carolina for 40 degrees in Ohio. Okay? This guy, we could do the same thing. I don't even think I need my calculator. This is another x, right? If you put 0 right there, what do you get? 31. So we get, so I'm going to say everything's the same here. Predicts 31, we'll say about 32 degrees, yeah? There's something dangerous about that. Think about the context here a little bit. Ohio, North Carolina. North Carolina's in the south. Ohio's not. Ohio's up by the Great Lakes, right? Stuff gets colder in Ohio. So this is saying if it's 0 in Ohio, it's 32 degrees, which is at freezing in North Carolina. Do you think it gets to freezing in North Carolina very often, ever? I'm sure it does, but not very often. This is a hallmark example of something called extrapolation. Did we have anything near 0 degrees in our data at all? Do we have any information about like stuff close to 0 in Ohio in there? There's nothing even close. The closest thing was what? 20? Yeah, it's the closest thing. Ohio, 0 degrees is far outside our data range. If someone asks you to make a prediction far beneath your data range, like this one, or far above your data range, you should tell them that's dangerous. I shouldn't be doing that. If it's close to the edge, okay. This is pretty far from the edge. Something else might change. This scatter plot that we saw a second ago might change. In fact, I think it is. It's probably going to like level off back towards freezing temperatures or do something different. And that's the danger here. So I'd say our model predicts 32 degrees or whatever, but this is a dangerous extrapolation. Why? Because we don't have any information about near 0 degrees. Okay? Last one we're going to predict, last thing for today, is we want to predict Ohio for 60 degrees in Carolina. Is this an X or a Y? This is a Y this time. You can use your model backwards like that. So now I've got to put 60 in for Y. So I'm going to do that up here. So I'm going to say 60 is a Y value. And I got to solve for X, exactly. It's going to take a couple steps, right? I got to do this.
Parker Graham, please report to the stage. Parker Graham.
And then what do I have to take that answer and do with it?
Divided by 60.
Yeah. fill in my math a little bit over here. Divide and you get x is 41.33. Make sure you get units on these when you're making your predictions. I'll see you next time.